All right, here we go with iChem Lesson 4 on energy, light, and electrons. This will really start to help us make the connection between our observations in the lab and our understanding of energy and what we now know about electron configurations and the organization of electrons in the atom and the ideas that we'll continue to build there. So 2 questions I want you to keep in mind while you're watching are: what color light has a higher wavelength, red or violet, the 2 ends of our visible spectrum, or what color light has higher energy, red or violet, again the 2 ends of our color spectrum. So first, some energy basics. You've seen this in physics, so I'm not going to belabor the labeling a wave. What I want to focus more on what a wave really means. So all energy travels in the form of a wave. And scientists measure the wavelength of the wave to identify its type of energy, to understand how much energy it has. There are 4 important wave words that are maybe in addition to the ones that you talked about in physics last year. So wavelengths is probably familiar. Get to know the symbol right there. Frequency, also probably pretty familiar. Energy, and the speed of light. There are 2 equations that represent waves. Again, maybe things you've seen before as well. First, the speed of light, c, is equal to the wavelength times the frequency. And the second one is energy is equal to h, which is Planck's constant, times the frequency. In chemistry, though, what we're really interested in is how much energy is coming out of an atom and how much energy is being put into an atom, in the case of the lab that we're going to talk about tomorrow, to achieve a particular color, the color that we see. So the 2 equations, again, are here on the slide. What I really want you to know is not necessarily the equation, but what we call in math and science the idea of proportionality. So this proportionality equation down here, you notice the equal sign is replaced by this proportionality symbol. It's kind of like a figure 8, but the far right end is missing. What it means is energy is proportional to 1 over wavelength. So they're kind of opposite each other in trends. As energy goes up, wavelength goes down. As wavelength goes up in value, energy has to go down. They're inversely proportional. So let's apply this idea to color and what we know about the electromagnetic spectrum. So this is what we know of. It's called the electromagnetic spectrum. We're going to focus here on this small part in the middle, which is our visible spectrum. The smaller wavelengths are violet, and the larger wavelengths are red. This is the colors that we can see with our eyes. So the whole spectrum includes all forms of energy, from gamma rays, the highest energy ones, to radio waves, microwaves, the lower energy ones, and everything in between. Before I give you kind of the answers to our driving questions at the beginning, let's look at this proportionality again and look at red. Red is up here with the higher wavelength. So it has the bigger wavelength. So remember, it's inversely proportional. Big wavelength means low energy. So red has the longest wavelength, but if I plug this into my proportionality, as it has the lowest energy. And on the other end of the spectrum, violet has the smaller wavelength. So if I plug it into my proportionality, the highest energy. So red is lower energy than violet. Green, sort of somewhere in the middle. Blue tends to be higher energy too. Some of you may have heard that the hottest stars in the galaxies are seen as blue, so that may tell you that our star, the sun, is relatively cool because we see it as orange. You can kind of start to relate color to energy by that, remembering that violet, highest energy, red, lowest energy. We're going to connect it real quick to atomic structure and build on this idea tomorrow in class with our lab. So first, absorption. It's the idea that atoms, specifically the electrons, can absorb photons of energy, where a photon is defined over to the right here as a quantum, which in layman's term is a piece of energy. With higher energy, the electron, when it's given, absorbs energy. That electron moves from its normal energy level, which we call a ground state. So write this, you need this definition. The ground state is the lowest allowable energy level for a certain electron. When it absorbs that energy, it goes to a higher energy level called an excited state, which is a temporary, keyword here, high energy level for that certain electron. And this is the whole idea behind absorption. You don't need to write all of it down, just this key point about absorption here, and then the 3 definitions. Pause if you need more time to write. Again, remember it's a temporary higher energy. So eventually the electron will release or emit that energy that was recently absorbed. The emitted photon of energy leaves the atom in form of light. If it falls between that visible range, that visible light spectrum, we will see it as visible light. And this is exactly how we observe the different colors in fireworks. The energy that's put into the fireworks causes the electron to go to a higher energy level, and when it drops down to a lower energy level, we see the beautiful colors of the fireworks.